Well, we will get started, everybody. So definitely see some familiar faces, but I also see some new faces as well. So for those who don't know how we do this, we will sit up here and talk for probably 25 or 30 minutes, and then I'll turn it over to the audience for question and answer, and we'll do that for maybe 15, 20 minutes as well. So today, we are lucky to have Dr. Nick Foukal with us. Dr. Foukal is an assistant professor in the University of Georgia's Department of Marine Sciences and a member of the faculty here at the UGA Skidaway Institute of Oceanography. He earned his bachelor's degree in engineering science, modified with economics from Dartmouth College, his master's in oceanography from the University of Maine, his PhD in earth and ocean sciences from Duke University. And prior to joining SKIO in 2024, Foukal was an assistant scientist at the Woods Hole Oceanographic Institution. He is a physical oceanographer interested in where, when, and how the ocean stores and transports its heat. So please welcome Dr. Nick Foukal. So to start off, for the people who aren't oceanographers in this room, can you give us a general explanation of the AMOC? What is the AMOC and why should we care about it?
Sure. So the AMOC is a bit of a mouthful. So it's the Atlantic Meridional Overturning Circulation. Actually, I'm going to show the slide. So it's basically a system of ocean currents that's in the North Atlantic. It actually extends into the South Atlantic and also into the Arctic as well. But the sort of center of focus is the North Atlantic Ocean. And so when you, I guess there's a lot of currents in the North Atlantic, and when you average them all together, what you end up with is a net northward flow in the upper sort of 1,000 meters, and then a net southward flow below that. And so this overturning circulation has kind of been, the analogy that's been used in the past has been a conveyor belt, which is a sort of a good first order approximation of what's going on. I will just say that with any oversimplification of a complex system, it has its limitations, and we'll talk about some of the limitations of that analogy in a second. But it's generally this overturning circulation in the North Atlantic. And it's shown here, so you can see the Gulf Stream moves a lot of warm water. So those are the red currents northwards. They give off their heat to the atmosphere, they cool off, they become denser, and they sink, and then they return southwards. And so that's this sort of overturning circulation. And if you think about it on a global level, you know, the Earth receives a lot of energy at the equator, and less so at the poles. And the ocean and the atmosphere together redistribute that heat poleward. So this happens in the southern hemisphere and also in the northern hemisphere. And in the Atlantic Ocean, the AMOC, this overturning circulation, does a lot of that heat transport. It moves heat away from the equator, and that essentially extends the habitable land in terms of, you know, by us humans. It cools off the equator and then it warms up the high latitudes, and so it extends this sort of latitudinal range at which we can live. Trying to think of what else I wanted to say. Oh yeah, so you know, something I gave a talk at this venue last year, and I talked quite a bit about the subtropical gyre and the subpolar gyre, and that's shown here in these two sort of arrows that are relatively small compared to the AMOC. So the AMOC is definitely emphasized in this circulation, whereas the gyres are de-emphasized. I just want to mention that the subtropical gyre is about 10 times stronger than the AMOC. So despite the fact that the way that it's displayed here, the gyres are the dominant circulation pattern. The other little kind of tidbit of information that's kind of fun is that in the South Atlantic, there's also a net northward heat transport. So this warm water is also going towards the equator. And actually, this is the only place in the Earth where there's actually the ocean or the atmosphere moves heat towards the equator rather than away from the equator. So the atmosphere actually has to counteract that and move more heat away from it at those in the South Atlantic. Let's see. So I mentioned that I gave a talk last year about this, and I just want to differentiate a little bit about what I talked about last year versus this year. Excuse me. And so basically, today we're going to be talking a little bit about why, how we measure the AMOC. And I'll talk about it sort of as a community rather. I'm not going out there individually measuring the AMOC. It's a massive system, right? So this is definitely a community-led effort. I'll talk a little bit about projects that I'm leading that are sort of smaller scale focus. But the general thing I want to introduce here is what's called the stream function. And I will warn you, this is a little bit of a complex idea, but when we go from this map view of the AMOC to measuring the AMOC, it's actually kind of a critical component to this. So when you average all the velocities, so if you go from Savannah over here by the Gulf Stream all the way across to Morocco, and if you average all the velocities in that surface layer of the ocean, you end up with one component of the stream function. And then you do that at every single depth level, so below the surface, all the way down to the ocean bottom. And you cumulatively sum that velocity. And you come up with a stream function. And this is basically what you're doing is you're collapsing this three-dimensional ocean circulation into 2 dimensions. And the reason you want to do that is because it simplifies the system. And so instead of measuring all these various currents, you can actually collapse the system and measure a few critical spots. So the analogy that's kind of useful here is that this is sort of like a weather map. So if you're familiar with looking at the weather map in the newspaper, or I guess online now, you can see a low pressure or high pressure system, and you can infer the circulation just from the sense of that low pressure or the high pressure. And the same thing is happening here with a stream function. You can get the sense of the rotation around this stream function just from looking at there's a high right here. So this is relatively high. So this is a positive stream function, and that gives you the sense of the rotation. It's sort of like if you're looking at a topographic map of a mountain range, you can see where there's sort of highs and lows, and the contours, the spacing of the contours tells you how steep the slope is. Here, the steepness of the slope tells you how fast the ocean velocities are. And so these locations here where the contours are relatively close together indicates that the velocity is relatively fast. And then the contours kind of spread out, and that indicates a relatively slow circulation that's more diffuse, and then a return flow. And I haven't introduced the axis here. This is depth. So as you go down in the water column, so this is the surface waters, and then as you go down to 4 kilometers depth, this is the bottom of the ocean. And so this sense of the rotation is that you have warm water going up in the surface layers, and then cold water coming down in the subsurface layers. So this is the same information on that stream function, but just kind of tilted on its side. So previously you had the latitude on the y-axis and depth on the x-axis, and we're basically just turning this on its side. So now you have the South Atlantic on the left, North Atlantic, and the Arctic, and depth is on the y-axis. And these currents, or the arrows, show the sense of the currents. They basically just go around this high in the stream function. So this relatively high value, so this is 20 sverdrups. So a sverdrup is 1 million cubic meters per second. It's our unit that we use in this field. And it just shows that there's a relatively high pressure or high stream function, which shows the circulation around it like this. Okay, so that's the basics of how we actually go from a 3-dimensional circulation to something that we can actually get our hands on in terms of understanding its dynamics. I will just say, if you didn't follow that, I think the rest of the talk, hopefully we're going to be talking about other things that, so don't get up and leave yet. But I think it is kind of an essential part to how we measure the AMOC. The one other thing I just want to mention here is, so actually I should just jump back and just say, so I drew these lines at 26 degrees north and at about 58 degrees north. So these are these vertical lines. And what they correspond to is where we have measurements in the actual ocean. So there's 2 lines of moorings. One, I'll show in a second, goes from Florida to Africa at 26 degrees north. And then the other one is further north. And so this picture that we get from this stream function is from a model. And so in the model, we know the velocity field everywhere in the model. And so we can come up with this stream function. We can calculate it in the model. Of course, the question is, does that model represent reality or not? But in the observations, we have these two dedicated mooring arrays that measure the AMOC at 26 north, called the rapid array, and the OSNAP array at about 58 north. And so that's what's shown here. So this is what sort of a slice through the North Atlantic looks like. So there's kind of a plan view or a map view on the top, and then a slice through the ocean. And you can see each one of these vertical lines is a mooring. So there's a set of moorings on the western boundary over in the Gulf Stream, and then on the eastern boundary. And they just they can calculate the net transport across this whole line just with moorings on either end. And we can talk a little bit about that, how you do that. And then at OSNAP, they do the same thing, but there's a line of moorings that goes from Canada to Greenland, and then Greenland over to Scotland. And so it's not quite at one latitude. It has a little bit of a latitudinal break to it. The rapid array has been in the water since 2004, and the OSNAP array has been in the water since 2014. So that's the kind of coverage that we have. That's more than what you asked me, but I'll let you ask the next question.
I think just a couple clarifying questions, there, just like to break it down and make it a little bit more simple. So you mentioned that this is a collective effort. It's not just you. There are a lot of scientists who are working on this, who are putting these moorings in the water at various locations to collect this data that allows us to track the movement of this system.
Yep.
So can you tell us a little bit more about maybe the specific work that you do? I mean, I know in a week or two, you're going up to Greenland, right?
Yeah.
And you're going to go on a giant research vessel and go drop some moorings in. So can you talk a little bit about your work and the projects you work on? Yeah.
Sure. Yeah. So one project, I am involved in OSNAP. This is, I should have defined, OSNAP stands for Overturning in the Subpolar North Atlantic Program. It's a big international effort, as Jackson was just saying. This is, I think there's 6 nations involved. The U.S. is a big part of that. But we, the mooring array that I'm part of is this one little part that's on the West Greenland side. And there's Canadians and Germans that measure the Labrador Current over here. There's another U.S. component led by Harvard over here. There's a Dutch component, and then a University of Miami component. So anyway, you get the idea. There's a huge international collaboration that's measuring this system. It's not easily done by individual programs. So each PI, each principal investigator who's part of this program, does publish data on their own individual current. And so there's some really important parts of, like, for example, the West Greenland mooring array that I will be part of that is measuring the West Greenland current. And one of the big questions that comes out of that is, how does the fresh water that's coming off the Greenland ice sheet from the melting on the Greenland ice sheet affect this whole system?
Right.
So we're measuring that directly in the West Greenland mooring array. The other, let's see, I'll just jump to this. So this is the project that Jackson was just talking about. So next week, we're going up to Bergen. Claire is in the room. She's going to be joining on our cruise. We're going on a Norwegian icebreaker from Bergen, just right behind this legend, over to this site off of East Greenland. So this is Greenland here. Here's Iceland. We're measuring the East Greenland coastal current. So we put a set of moorings up there last summer, I guess September last year, and we're going back to collect them. So there's, that's another component where we're actually measuring the fresh water that's coming down the East Greenland shelf with the hope of understanding how it impacts the AMOC, this large-scale overturning circulation. So, we're putting 6 moorings in for that array. There's a Norwegian component that has another 6 moorings. And then a German component that has a 13th mooring. So together we have 13 moorings in a line measuring this one component, which is the East Greenland current and the East Greenland coastal current. And so for that project, we're really interested in how much fresh water is there. For example, no one's ever measured this coastal current, which is when I got into oceanography, I kind of thought we knew these things. The more you get into these fields, you realize that there's kind of massive unknowns. And one of the reasons for that is that ice is really difficult to work in and around. And so typically if you put moorings in the water around here, they get swept away by the ice, the sea ice and the icebergs. And we will find out in a few weeks whether ours got swept away from the ice and icebergs. But anyway, yeah, so we put moorings up here, and we're measuring this coastal current that is just, one individual component, and we're one, I guess I'd say, a proposed mechanism for what could cause variability in the AMOC. So there's this hypothesis that the fresh water that is coming off the Greenland ice sheet and also out of the Arctic could inhibit the sinking that occurs in the North Atlantic. So this sort of diffuse sinking that I was talking about a little bit in the stream function, if you introduce fresh water into the system, fresh water is very buoyant. It wants to sit near the surface, and it could slow down that sinking process and slow down the system. So we're kind of going after individual components in these sort of, I would say, smaller scale projects. And then there's these larger scale projects like RAPID and OSNAP, which are measuring the whole system as a whole and trying to get, in a sense, it's a bit of a monitoring campaign of trying to figure out, what is the AMOC doing and how is it changing on the more modern timescales, the past, 10 to 20 years.
Yeah. Before we talk about, I want to talk about the instruments that you're using. We've mentioned moorings a lot, but before we do that, can you speak a little bit more? You already mentioned some of this, but a little bit more about the impact that the AMOC has on temperatures and everything else in our world.
Yeah.
Like a common example is England, right?
Yep.
How it changes the temperature there. So can you speak a little bit more
about the impacts? Yeah, absolutely. So actually, I need to correct the record from what I said last year too.
Okay.
So so the big impact is that it moves heat northwards. The AMOC moves heat northwards. It keeps Northern Europe much warmer than it would otherwise. And some estimates, it's maybe 10 to 15 degrees Celsius warmer than it would otherwise, which is a big impact. So if basically, that's the first order impact, is that it moves heat northwards. The atmosphere picks up that heat over the North Atlantic. It redistributes that heat over Norway, UK, and it keeps that area much warmer. Just as an example, if you go over on the east side or the same latitude on the eastern side of Canada, you hit Labrador. So that's just a good analogy of the different climates that you can see at one latitude. And the ocean plays a huge role in why there is that divide in the climates. There's other impacts about rainfall in the equatorial regions, and the one, I won't go into that into too much detail because I talked about it last year, so I'm sure you all remember it. And then the part that I want to correct the record on is that I said there weren't that many impacts locally in Savannah. And one thing that I've actually become a little more appreciative of here, since I only moved here 2 years ago, is sea level. And this area is obviously very low lying, and the AMOC does have an impact on local sea level here. So if the AMOC were to weaken, or in some scenarios, people have predicted that it would collapse down to zero, you would basically end up with a sea level rise, in addition to other factors like ocean warming and ice melt, another 10 centimeters of sea level rise on top of that. So that might happen over the next 100 years. So it's certainly not going to happen overnight, but it is another compounding factor that's going to add more sea level rise locally here on the east coast of the U.S. It's distributed across the whole east coast of the U.S. This area south of Cape Hatteras is particularly vulnerable, or just more impacted, I guess, by the sea level. But that's a part that I didn't really touch on last year that I wanted to make sure that there is a local impact. It's just not on the temperature and the precipitation that gets a lot of the headlines when people talk about the AMOC.
Right. So measuring the AMOC, how you and all of your colleagues measure the AMOC. Can you kind of take us, you mentioned the moorings. Can you kind of take us on a tour of all of the instruments that you and your colleagues use to measure the strength of the AMOC and to see if it will be collapsing and that sort of thing?
Yeah, so just I think this kind of hopefully gives a little bit of perspective of what we're looking at. So this mooring array that I was just talking about on East Greenland, if you take a slice to the ocean, so this is depth and then distance from the coast here. So this is essentially the coastline over here on the left. So Greenland would be right here. This is the ocean water that we're measuring. And our moorings are these first 6 ones, 1, 2, 3, 4, 5, 6 in green. The Norwegian ones are measuring out here in the deeper waters at the shelf break. So this gray area is the ocean bottom. And this is the shelf break. So right about at 400 meters. So it's a pretty deep shelf here. You know, the shelf is, I don't know, Catherine's here, maybe tens of meters deep. Here in Greenland, it's 400 meters deep. And so this is still a lot of water that we're measuring here, but it's still relatively shallow to what's happening at the shelf break. So when we measure, when we talk about what are we doing, in terms of the instrumentation, we put a series of what are called CTDs. So these are conductivity, temperature, and depth measurements. So they measure the conductivity of the water, which we can infer the salinity from the conductivity, the temperature, which is straightforward, and then the depth of the water. It's actually, you measure pressure, but either way, I think you get the idea. So we're measuring temperature and salinity and pressure. And with those 3 variables, we can infer the density of the water. So density is really what's going to be driving most of these currents. So when you have gradients in density in the ocean, that excites a force, a pressure gradient force, which moves the water. So if you can look for gradients in density, that'll give you an idea of where the ocean currents are. The other thing that we're directly measuring velocities at a few sources. And so these triangles are what are called ADCPs. And I'll show you a picture of what those look like right here. So these ADCPs are these instruments right here. So this is a whole instrument that goes on the bottom. This is actually a schematic of what that looks like. So this thing will land on the bottom. It kind of looks like a lunar lander. So it sits on the bottom, and you have instrumentation that's looking up at the water column above it. So these ADCPs are sending out acoustic pulses. So the ADCP stands for Acoustic Doppler Current Profiler, and it sends out a acoustic pulse in a prescribed frequency band. So it knows exactly what that frequency band that it's putting out a signal in it is, and then it listens for 2 things: how long it takes for that backscatter to come back to it, and that tells you how far away any particles are in the ocean that might have pinged back, essentially. So they're not pinging back, they're just reflecting back. Just to be clear, there's no creatures that are pinging back. Oh, there's some whales out there that might be pinging back. But anyway, now I'm digressing. So basically, they're sending pulses of acoustics, so sound signals, off of particles in the ocean and getting a return signal that tells you how long it takes to come back. That tells you the distance away from the instrument, but also the Doppler shift. So if you remember back to Doppler shift, or it's, the analogy is when a train goes by, it's very high frequency when it's coming towards you, and then low frequency as it moves away from you. So it's listening for that Doppler shift, and that'll tell it how fast that particle is moving away from or towards your instrument. And then there's 4 beams, so there's 4 heads here that are all doing this at different angles, and they triangulate and give you a current at a range of depths away from your instrument. So you're actually directly measuring the velocities here, which is exciting because there aren't many places globally where there's actually these ADCPs in the water. They're relatively expensive, that's why. And then we're also measuring temperature and salinity and pressure. So that's a CTD, a moored CTD right here. So this all sits at the bottom, but we also will have a tether, so a line with floats on them, and that's shown here. So there's a big buoy that sits at 30 meters below the surface, and it's got instruments along the wire that we measure the temperature and salinity at a few point places. So that's the number one thing we're after is number two things: density and velocity. And to measure density, you need temperature, salinity, and pressure. So that's kind of the instrumentation. I think that was all I had for the instrumentation. Yeah.
Okay. You also have mentioned in our previous conversations, you've mentioned that satellites are being used.
Yeah.
Correct. So can you speak a little bit about how satellites play into figuring out these measurements?
Yeah. So this is there's many different types of satellites, right? So there's there's passive satellites that have been around since the late 70s that are just measuring sea surface temperature, for example. And they're basically just taking pictures of the ocean surface at prescribed frequency bands, and then they can back out what the temperature is from the brightness in each of those different frequencies. So that technology has been around for a long time. And there are methods that have been proposed to use sea surface temperature as a proxy for the AMOC. That's a whole nother discussion. I don't know if I will have time for that. But that's an indirect method. So that would be measuring temperature and inferring what the AMOC is doing. So if you measure temperature variability. So that's been around for a while. And the advantage to that is sea surface temperature measurements have been around for a long time. And actually, even before satellites, sea surface temperature is probably our best measured variable in the ocean historically. So there's some advantages to that. The more recently, there's been a development of these sea surface height satellites. So sometimes they're called satellite altimeters. And the early one, so this is a very advanced one that I'll talk about in a second, but the early versions of these just had a laser that they bounced off the ocean surface, and again, just timed how long it took for that beam to come back to the satellite. And from that, they can, and also very accurately measuring where the satellite is through GPS, they can figure out how high the sea surface is. And so if you go to the beach, you can know that there's a surface waves and there's variations in sea surface height. But on larger scales, there's much bigger variations in sea surface height that drive our ocean circulation. So just as an example, when you cross the Gulf Stream, you go off Savannah, you go across the continental shelf, you actually go up a hill that's about 1 meter high as you cross the Gulf Stream. And that meter of sea level gradient is what causes the Gulf Stream to move in the first place. So if we can measure the sea surface height globally, then we can infer what the surface ocean circulation looks like. And we've been doing this since the early 90s. I think right now there's on the order of about 10 satellite altimeters that are up orbiting right now, measuring the sea surface height constantly. The disadvantage of these satellites is that they measure one pinpoint measurement underneath the satellite as they go along, and they don't have very good spatial coverage. So what ends up happening is there's some post-processing that grids all this data onto a common grid, but you lose a lot of the spatial resolution when you do that, and so it becomes pretty coarse. And I can show you an example in a second, but in order to address that, there's this new satellite called the Surface Water Ocean Topography Satellite. So in addition to this nadir altimeter, which is what the old satellites had, just this one point right below the satellite, we are now getting these swaths of data on either side of the nadir. And we're getting for every pass, it's on the order of 1,000 times more data for one satellite than we were getting from these 7 satellites, this constellation. So it's a complete revolution in satellite oceanography, specifically physical oceanography, because we're measuring the ocean currents using this. And it's been around, it's been orbiting since 2023. And it's remarkable. I'll just show you an example of one sort of, this is what the previous, so this is North Carolina, there's Cape Hatteras. This is what the gridded product looked like in terms of highs and lows. This is sort of very low definition. And there's this swath that's shown from one SWAT pass. And that same information is shown here with the SWAT data. So the analogy I like to use is it's like going from high or low resolution TV to high resolution TV, right? I mean, you can get so much more structure in the sea surface height patterns. And so you can resolve circulation features like the Gulf Stream that were barely resolved using this previous data set. And so the reason this comes up into the AMOC research is that we have very good measurements of the open ocean. As you get across the Gulf Stream, from the edge of the Gulf Stream, the eastern side of the Gulf Stream, all the way to Africa or to the eastern side of the basin, we can infer that circulation pretty accurately using things like profiling floats or gliders or other technology that we have a pretty good idea of. But these western boundary currents, the Gulf Stream, the Kuroshio, the East Australian current, are very concentrated flow, and they're very important to these large-scale circulation patterns like the AMOC. And so if we can get a handle on their variability from satellites, it'll give us a lot more confidence in our ability to reconstruct the AMOC. So that's the biggest sort of step change in satellite oceanography that I've seen in my career, which is relatively young, but it's still it's been a big change. The other thing I'll just mention that other satellite technology that gets used a lot in the AMOC research is surface winds. So you can actually measure surface winds from satellite using scatterometers that send out pulses of energy and look for the scatter back. And depending on how scattered the backscatter is, it tells you how rough the surface of the ocean is, and they can infer what the winds are doing just from the surface of the ocean roughness. So there's all sorts of kind of interesting technology that's been developed from satellites, and we use those wind measurements quite a bit in the AMOC estimates at RAPID and at OSNAP.
Oh, okay. So that's what I was going to ask. Can
Yeah.
you speak a little bit more about how the measurements from these instruments that you've shown with the satellites kind of come together to form a bigger picture?
Yeah, right.
Yeah.
So actually, I'll go back. There's in that RAPID, let's see. Here we go. So this is the time series from the RAPID array. So this is the AMOC time series. There was a big dip in 2010, for example, and there's some seasonality. There's a lot of variability. There actually is a long-term trend towards a slight decline since 2004. It's debatable whether that's statistically significant or not, but there is a slight trend in that. What's shown here in these other data points or the other curves is the Gulf Stream. So that's actually interestingly measured by a old telephone cable that goes from Florida to Bermuda. And okay, let me just talk about winds for a second, and I'll come back. And then there's the Ekman. So this Ekman circulation, or this is the wind-induced flow. So this is in the top 50 meters. So the relatively shallow layer in the top of the ocean that is purely wind-driven, and that's measured just from satellites.
Oh, okay.
So there's no direct measurements, not that I'm aware of, that go into this green. And then there's another part that's called the upper mid-ocean, which is this southward return flow. And the point is that these three curves, the pink, the green, and the blue, add up and they come up with the red. So you add up these individual components, one of which is the purely wind-driven one, and that adds into the AMOC. So these wind-driven or wind measurements from satellites are going directly into these AMOC measurements. Okay, I'll just say one quick thing. The telephone cable, they are measuring the voltage difference between Bermuda and not Bermuda, Bahamas and Florida, and they've backed out a relationship between the voltage difference across this old telephone cable and the volume transport of the Gulf Stream. So basically, Earth has a magnetic field, and if you have a polarized fluid, which is water, flowing through a magnetic field, it induces a voltage, and that voltage, you can actually measure the variability in the voltage across this telephone cable. Unfortunately, it was a fantastic technology because it was essentially cost $0. It was just an old telephone cable that's sitting on the bottom of the ocean. Unfortunately, it just recently broke. So that's the disadvantage if you're not maintaining it. But it gave us daily measurements of the Gulf Stream since 1982.
Wow.
Yeah.
So I want to turn it over to the audience for Q&A. But before we do that, just to kind of put a little bit of a bow and go back to the top of our conversation.
Yeah.
I know a lot of the audience members may have heard of the slowing of the AMOC, and we spoke about how that might influence various things. So can you kind of give us a high-level overview of where we stand in terms of, is the AMOC slowing? Is that something that is a concern right now? Yeah.
So my view on this actually changed about 2 weeks ago.
Okay.
And I will say this is a rapidly evolving field. There's probably 2 or 3 new papers that I have to read on this every week that come out.
Yeah.
So it's it's hard to give you a concrete answer on that. The reason that my viewpoint changed quite a bit on this was that I went to a conference and there were some paleoclimate folks. So these are people who study the oceanography or the climate system over thousands of years. And the primary motivation for this mechanism for why we think the AMOC will slow down into the future is because of fresh water coming out the Greenland ice sheet. I already alluded to this. But the reason we think that could actually cause a collapse or the real sort of fast change or tipping point in our climate system is due to the literature that's come out from this paleo or the paleo groups around the world. And they've said that basically as we came out of our last ice age, there were these changes, these rapid changes to our ocean circulation, most likely the AMOC, that caused changes in Greenland temperatures to change by about 16 degrees C over the course of about 10 years. So that's a huge change. And this is happening, 10 to 12,000 years ago. So not all that far back in our Earth's history. And the most logical interpretation of that was it was due to the AMOC change. Now people are less confident that that was actually due to the AMOC. And I will say I'm not a paleoclimate person, so I'm not going to be weighing in on this individually, but just speaking from the consensus I got from this workshop was that there's very little confidence that the AMOC has ever collapsed or really, if you want to use the word collapse, or declined in a significant manner, that there's other ways of explaining some of these signals that they're seeing in sediment cores and ice cores. And I was really blown away by that, because that's sort of a bedrock of this whole field of research, is that this AMOC is a tipping point in our climate system, and it's potentially unstable. So I would say that is really changed my view that I thought it was sort of a foregone conclusion that AMOC would decline out to 2100. Just that's what our climate models tell us. But I'm a little bit less confident that the mechanisms that we think would cause that are really actually going to be happening into our future. So that's potentially good news. I will say there's plenty of bad news in climate predictions, so don't hang your head on that. But yeah, that's where I'll end there.
I feel like that might stir some questions, so
Sure.
I'll turn it over to the audience.
Oh yeah.
Any questions out there? Yeah.
So the sensor on the bottom, what you said, is measuring particles in the water column to determine velocity. What particles are they? Is it biological? Is it salt? What is it?
As a physical oceanographer, I call them scatterers, but that's a physics interpretation. There's biology in there, so there's phytoplankton, zooplankton, other things that are raining out. So there's marine snow. There's all sorts of things that are just in the ocean that are backscattering back to our AECPs. Sometimes I call them critters, but that's as biologically focused as I get. Now, the reason this comes up quite a bit is, especially as we go to high latitudes in the polar environment, especially under sea ice, there's not a whole lot of biology, or not as much biology to reflect back to our instruments. And if the water becomes really clear, which it does in the winter time, we don't get a very good scatter back. And we end up with these large gaps near the surface of the ocean because there's not good returns. So it is an issue. But in general, globally speaking, it's a great technology and something that the fact that you can measure current velocity without being in situ, actually measuring the flow, is a huge development, because there's been a lot of research and interest into whether our moorings are actually disturbing the flow. So by the fact that you're measuring it, you're disturbing it. That's obviously maybe a small detail when you're talking about something like the AMOC, but if you're trying to measure really weak flow, it is something that is tricky to do. So if you can do it without having an instrument in the water at that depth, it's a huge technology, right? A huge improvement in the technology. But yeah, so I will, to get a more definitive answer to your question, I'd have to defer to the biologists in the room, but there's different scatterers. There's sometimes when they're there, sometimes they're not there.
You mentioned early on that pool shape around the equator was, I think you said 10 times more powerful than the Gulf Stream. Does that mean the currents 10 times more?
So, okay,
that's a pretty rapid.
So the Gulf Stream is primarily part of the subtropical gyre. So that gyre that I was talking about that's 10 times stronger is 90% of that water is part of the subtropical gyre. Only about 10% of that water is actually part of this AMOC. So the Gulf Stream contributes to both of those circulation patterns, and that's one of the reasons why it's so strong, is that it has this addition of these two components. So the it's not 10 times stronger than the Gulf Stream. It's 10 times stronger than the AMOC. Does that clarify things, or is that, no? Okay. Sure. Let's see if actually this is. Actually, this picture will work. So this is the Gulf Stream right here. And the Gulf Stream separates into what's the gyre. So that's the recirculation southwards here. Versus the part that goes northwards, and that's the part that's the AMOC. So the Gulf Stream is the addition of the gyre and the AMOC together.
Is it true that the AMOC moderates the temperatures in in like United Kingdom area?
Yes.
And what about, does it go down into Europe, France, and places like that? Because I noticed we were in Paris a couple of weeks ago, and we were at latitude 49, and it was warm compared to what you'd expect on this side.
Right.
And I guess one question I've always wondered is if I'll call it the Gulf Stream for simplicity, is warming up Europe and UK, how come it doesn't have that same impact on the coastal United States, like North Carolina, Virginia, it doesn't, you know?
It does. I mean, it certainly does keep this area warmer than it would otherwise. It changes also the precipitation patterns. It's also why you get some nor'easters in the winter. So it changes. One of the biggest impacts, the primary impacts of the ocean on our climate occur in the winter. So the atmosphere would be much colder, but it retains some heat because the ocean is constantly giving off heat to the atmosphere. The ocean has a longer sort of thermal inertia than our atmosphere. Some people refer to the atmosphere as sort of the nervous system. It's ameliorating sort of low frequency. So it definitely does impact locally, but in terms of why it's impacting Europe more so, especially at high latitudes, that's because of the wind patterns. So if you look at the winds, why there's hurricanes come by here, they go to the northeast, and that's because the westerly winds go from North America over to Europe. And so they pick up that heat and they distribute it over Europe, and not as much over Canada and the US.
I noticed, I used to be a marine engineer in the Merchant Marines. And when we would be out here near the Gulf Stream, we would float in and out of the Gulf Stream. I could tell by the seawater temperature, it would drop and would come right back up and stuff like that. So I imagine as the stream goes, or AMOC, whatever, goes up north, it kind of spreads out more so. And because it seemed to be fairly sharp from what I could tell, it would drop up, it would go up and down pretty significantly in a short period of time. And I just was wondering if it does, it must spread that out a little bit more as it goes further north.
So right off the Savannah coast, it's a confined region. So it's a western intensified current. So it basically is transporting almost as much water in. So the Gulf Stream is about 100 kilometers wide. And then that same amount of water is coming southwards from the eastern side of the Gulf Stream, from here all the way to Africa. That's about 1,000 times longer distance than the Gulf Stream. And so all this flow is very concentrated in the western boundary in the Gulf Stream, and it's very diffuse and distributed over a very large area east of that. And that's the gyre circulation. There's a little bit that gets pushed net northward, that's the AMOC. But in general, most of the Gulf Stream water comes southwards. It returns southwards over this much more distributed or diffuse flow.
One last question. Sure. Is there a similar phenomenon in the Pacific Ocean?
The gyres are the same. So there's the subtropical gyre and the subpolar gyre in the North Pacific. There is this concept called the PMOC, or the Pacific MOC, and right now it's about 0. So, but if you look in the paleo literature back, 50,000 years or so, there have been times when the PMOC has been active, and it just depends on sort of the background climate state, essentially, whether there's more AMOC or more PMOC.
I may be mistaken, but it sounded like what you said is that Greenland experienced a rapid temperature increase of 16 degrees Celsius, and it was not because of the AMOC. So what the blazes caused that?
That's a great question. That was actually exactly my question after this workshop, because you can, it's very easy to shoot down concepts, right? To have ideas of why, why it's not the AMOC. If somebody puts forth an idea, it's kind of easy to poke holes in it. But I have not heard a convincing alternative explanation for those changes. So, and that's, if you go back, so Wally Broker was a very famous scientist at Lamont Doherty in Columbia, and he was one of the people that put forth this idea that it has to be the AMOC, that there's no other way to explain these rapid changes in our Earth's climate without inferring some part of the AMOC. And I generally agree with that. I mean, it's hard to think of another system in our climate that's really focused on Greenland too, to cause such large changes on such short timescales. So I think maybe if I were playing devil's advocate a little bit to that idea that you don't necessarily need to collapse the AMOC. So it could be AMOC-induced variability, but maybe not to the same degree that it was appreciated before. So you don't necessarily have to turn the AMOC off to get those changes. Maybe you change the depth of the AMOC. So whether you shoal the AMOC or you change where that deep water formation is happening, the sinking is happening, if you move that southwards, that's a possibility. So, when we're talking about these paleo timescales, you have to remember sometimes entire subpolar North Atlantic or the Labrador Sea, which is between Canada and Greenland, is covered in ice. And that's a completely different climate system that we have right now. So there's other ways of changing the AMOC rather than just turning it off. And that's maybe where the nuance comes in, how you can explain some of these large changes. Yeah.
One more question. Do you have any idea whenever the ice age we're in right now is going to end?
Ice age.
Well, all the ice melting. Yeah.
From zero, I don't think it's going to happen anytime soon. But yeah, I don't know where we are in our ice age cycles right now. I should put that. Is that what you're asking?
Yeah. Aren't we still in the last ice age? Aren't we still in that?
Well, we come out of the last ice age about 10,000 years ago.
Yeah. Came out of it.
Yeah.
Okay.
So the velocities, what changes the velocity of the AMOC? Is it seasonal? Is it, what you really had talked about, what those velocities are or how they vary, what causes them to vary?
Yeah, it's still open question to some degree. So there's definitely a huge wind component. So the winds impose a large signal on the seasonal timescales, potentially also the interannual timescale. So from one year to the next year, there's something called the North Atlantic Oscillation, which is a mode of variability in the North Atlantic that is coupled between the atmosphere and the ocean. And when the North Atlantic Oscillation is positive, it causes these westerly winds from North America to Europe to intensify. And that essentially spins up the AMOC. And so there's signals from that on short time scales. The question is, as we get longer and longer time records, and so that rapid array has been in the water since 2004. So now we're up to 20 years, it would take. And we're starting to see some of these lower frequency things like decadal variability that probably are not as much induced by winds that are responsible for shorter frequency, higher frequency variability. So it's a long answer to a very simple question that I don't think we fully grasped all of the complexities of that. I mean, I have a student right now who's working on the season cycle. So just understanding why it is that this, that's stronger in the late summer and weaker in the sort of late winter. We're trying to figure that out. It's shocking to me that no one has really, got a good understanding of this yet. So a lot of this stuff is pretty new research. We're getting our hands around a lot of this. These direct observations have really revolutionized AMOC research. We're not going from indirect measurements of sea surface temperature. We actually have direct measurements of the ocean velocity.
So I was curious, I know you're going on like an icebreaker expedition, but I was also curious about a rover expedition that was on.
Yeah.
What is that? Is that?
Yeah, so it's the same one actually. So Rover is the project that we're talking about. Mm-hmm. Yeah. So Rover is this Norwegian group that's going out, that's leading this cruise that we're on. We're essentially piggybacking onto a cruise that's already going up there. There's a Norwegian group that are on a Norwegian icebreaker where we have a small team of American scientists on it. So ROVER stands for Resilient Overturning in a Warming Climate. And that's the idea there is that as we have less sea ice, especially over the East Greenland current, there's actually more deep water formation or dense water formation that's happening over in East Greenland that was happening previously. So it's a negative feedback. So as we remove sea ice, we warm the climate, remove sea ice, it actually cause the AMOC to strengthen a little bit. Now that's a negative feedback, and the question is, does that negative feedback compensate for all these other positive feedbacks that would cause a decline in the AMOC as we are warming the climate? So that's one of the hypotheses we're trying to look at in that question or in that project.
I was also curious, so back to SW2. Are there any other parameters that have like significantly improved that you've been using, or what are some of the other applications for that satellite specifically that haven't been yet seen in, or maybe have been greatly improved?
Yeah, so SWAT, there's a huge amount of data that's coming out of that satellite, and what we're using it for is inferring the surface velocities. But there's tons of other groups who are trying to dig into the other signals in there. There's now that we're measuring sea surface height at 2 kilometer resolution with SWAT, so instead of something like 25 kilometer, we're down to 2 kilometer resolution. You can resolve things that you've never been able to see from satellites before. Things like small scale eddies that have a really big impact on the biology and the nutrients and sort of distribution of tracers in the ocean. And so there's been the part that I use SWAT for is a tiny little fraction of what SWAT is being used for. And I would say that there's just been a bit of a step change in terms of research into smaller scales, called the sub-mesoscales.
Mm-hmm.
Yeah.
I was just curious if you know, like the bathymetry of the ocean, how does that affect the ocean currents, or does it, or does it not?
Absolutely, it does. Yeah. So, and just as one example, there's a sill that goes from Greenland to Iceland, and then from Iceland to Scotland. So this is a remnant of basically the spreading sector that Iceland is part of the Mid-Atlantic Ridge, essentially. And that retains a lot of really dense water in the Nordic seas. So there's this very dense water that forms in the Nordic seas just sitting there. And it can't get over that sill. Sorry. Every once in a while, there's sort of overflow, a spill of this water that kind of comes over this sill. So that's just, constrictions of the bathymetry are a big portion of how bathymetry changes the ocean floor.
One or two more we have time for. Yeah.
Is it true that Greenland was noticeably warmer 1,000 years ago? I believe it was. And if that's true, then I would imagine it would have had some impact on all of this.
I don't know. That's a good question.
I mean, Greenland got a name. Yes. I mean, yes, I believe it was noticeably warmer.
Wow. Gosh, there's a group that I've worked with in the past that does study settlement in West Greenland. So like when the Vikings settled Greenland, there are time periods when there was more exposed areas essentially, so that settlements could exist on the edge of the Greenland ice sheet. So yeah, it's not crazy to me. Yeah.
One last.
Yeah. So how does El Nino impact all this?
I thought I'd get that question. It's tricky. There are definitely some direct impacts. So El Nino is a Pacific phenomenon. So the tropical Pacific, the water basically from the Western Pacific sloshes into the Eastern Pacific. So it has definitely impacts. The center of impacts is in the Pacific. It has teleconnections up to California and South America. There are studies that looked at essentially it excites planetary waves. So when you change the distribution of sea surface temperature in the Pacific, it excites planetary waves that propagate essentially over the pole and then come and impact the Atlantic. Mm-hmm. Do I have a ton of confidence in those results that they can actually tease out a signal apart from all the noise in the AMOC, so we were just talking about how there's a lot of high frequency variability in the AMOC, and I'm not completely confident that that is a fully robust, or I wouldn't be confident saying that there's a direct impact of the El Nino on the AMOC. There probably is one, but I wouldn't even know what the sense of that relationship is right now. But it's a good question. It definitely impacts Atlantic hurricanes. So that's another sort of teleconnection that kind of jumps over into the Atlantic. The AMOC in particular, there certainly you can find papers that show an impact, but I'm not 100% certain they're robust.
All right, well, thank you again to Dr. Nick Foukal.